Now in this video, we're going to be talking about measurement of heat energy. Now, basically, heat energy measurement refers to the quantification of heat energy exchanged between an object and its environment. And mathematically, we have the quantity of heat energy equals mc delta theta, where Q is equal to the quantity of heat energy, m is the mass of the object, okay, and C is the specific heat capacity of the object measured in joules per kilogram per Kelvin or joules per kilogram per degrees Celsius. Okay, M is the mass of the object in kilogram. C is the specific heat capacity of the object. All right, and then delta theta is the temperature change, which is simply the final temperature minus the initial temperature, theta 2 minus theta 1. So this is our equation for calculating quantity of heat energy from an object, okay, or of an object. Now the specific heat capacity was mentioned here. All right, what is the specific heat capacity all about? Now the specific heat capacity is the heat required to raise the temperature of a unit mass of substance by 1 Kelvin or 1 degree Celsius. The heat required to raise the temperature of just one unit of a substance by 1 Kelvin or 1 degree Celsius. And it is represented with the symbol C, all right, lowercase letter, small letter C is the symbol for specific heat capacity. Do not forget, specific capacity has to do with a change in temperature. It says the heat required to raise the temperature of a unit mass of substance by 1 Kelvin or 1 degree Celsius. Now for heat capacity, the heat capacity is the heat required to raise the temperature of a substance by 1 Kelvin or 1 degree Celsius. Heat capacity is the heat required to raise the temperature of a substance by 1 Kelvin or 1 degree Celsius. Now it is also referred to as the thermal capacity. It's also known as the thermal capacity, and most times it is represented with the symbol C. Okay, this is uppercase letter or capital letter C, and the unit of measurement is joules per Kelvin or joules per degree Celsius. Don't forget, the unit for measurement of specific heat capacity is joules per kilogram per Kelvin or joules per kilogram per degrees Celsius. Now, mathematically, heat capacity and specific capacity, they have a relationship, and we have that heat capacity is equal to the mass times specific heat capacity. Heat capacity of an object is equal to its mass multiplied by specific heat capacity. Okay, so these are just the basic equations you need to know under um, measurement of quantity of heat energy. All right, so we're going to be taking, okay, so we are going to be taking an exercise now. And here, exercise 1, we have that what is the quantity of heat that will be given out if a bar of mass 350 grams, if a bar of mass 350 grams, so we have the mass of the bar given to us to be 350 grams, is cooled from 95 degrees Celsius to 20 degrees Celsius. Okay, so here we have change in temperature theta 1, okay, to be 95 degrees Celsius. Okay, and then final temperature theta 2 equals 20 degrees Celsius. All right, so here our change in temperature delta theta will be equal to final minus initial, which is going to be 20 minus 95, and that should give us minus 75 degrees Celsius. Now in solving, we just make use of 75. This minus sign here is just there to tell us that heat was lost, because what we have here is cooling. All right, so heat was removed. So since we have heat loss, that's why we have a minus sign here. All right, so now we have M given, we have our change in temperature, then the specific capacity too was given, which is 380 joules, all right, per kilogram per Kelvin. Now, before we start solving, we need to ensure that all our units are in order. Here we have specific heat in kilograms. Here we are seeing our mass in grams. Okay, so we need to convert these grams here to kilograms, and to do that we divide 350 by 1000. Okay, and that will give us 0.35 kilograms. All right, so now we can go on to the question. They said, what is the quantity of heat? All right, you're looking for Q that will be given out if a bar of mass is this, code from uh, 95 to 20. They give us the specific heat capacity. All right, so we'll just go to our equation that relates quantity of heat with specific capacity, which is this. So we have Q equals mc delta theta. All right, so Q was given, okay, Q is what we're looking for. All right, and m is 0.35 multiplied by C, which is 380, multiplied by the change in temperature, which is 75. Remember, I said just use 75. I forgot about the minus. The minus there is just to tell you that heat was lost, or we have cooling. So we are going to have Q equals 0.35 multiplied by 380 multiplied by 75. Okay, and that will give us 9975 joules of heat. So this is the quantity of heat energy. All right, so that's the answer to this question. Now, next question here says the quantity of heat in a body of mass 800 grams. We have mass of object here to be 800 grams and specific heat capacity 150 joules per kilogram per Kelvin. Specific heat capacity was also given to be 150 joules, okay, per kilogram per Kelvin. When heated from a temperature of 30 degrees Celsius to 120 degrees Celsius, we have initial temperature to be 30 degrees Celsius to 120 final temperature. Final temperature to be 120 degrees Celsius. All right. So they say the quantity of heat is what we're looking for. So Q is unknown. All right. Now, before we go on to solve, we need to get our temperature change, which is change in temperature delta theta. That's equal to final temperature minus initial temperature. All right. Now, our final temperature is 120 minus 30, and that will give us, I think, 90 degrees Celsius. All right. So this is our temperature change. Now we go on to solve for Q, but please you need to convert your mass to kilograms. So we have 800, okay, divided by 1000, and that will give us 0.8 kilograms. So we're going to solve for Q now. We have Q, all right, remember the relationship between Q and specific heat capacity is Q equals mc delta theta, all right, and that will give us Q equals m is given to us, which is 0.8 multiplied by specific heat capacity, which is 150, multiplied by the temperature change, which is 90, and that will give us Q to be equal to 10,800 joules. All right, so that's option D. So this is our answer here. All right, now also, so far we've been looking at just questions that deals with quantity of heat energy and specific capacity. Q equals mc delta theta. There are some questions where you'll be dealing with quantity of heat energy and heat capacity. You just need to not forget that heat capacity is equal to mass times specific capacity. So in that case, we're going to have Q equals, rather than writing mc, we write heat capacity times temperature change. All right, so this is another very important equation. Now, our next question here says heat was supplied at the rate of 50 joules per second. Okay, rate of 50 joules per second. This obviously is power. All right, power is the rate at which work done over time. This is joules, which represents work, and then this is time, seconds, which represents time. So obviously, this is power. All right, power equals 50 joules per second. All right, for 1 hour 40 minutes. This is time, so we have time given to us to be 1 hour 40 minutes. Okay, they said what quantity of heat energy is absorbed by the block. Okay, we are looking for the quantity of heat energy. Now, basically, all we need to understand here is power is the rate at which work is done or the rate at which energy is expended. Okay, and here the heat energy we have is heat energy. So basically, as you can say, power is equal to quantity of heat energy all over time. This is also another very important equation here. So if we want to get the quantity of heat energy or the heat energy involved, we say quantity of heat energy equals power times time. All right, and power was given, but time here is in hours, 1 hour 40 minutes. So we need to convert everything here to seconds. So to do that, we need to understand that 1 hour is equal to 3,600 seconds. That's a constant. 1 hour is always equal to 3,600 seconds. So say we have 1 hour 40 minutes. That's like 1 hour plus 40 minutes. That's what 1 hour 40 minutes means. So we're going to have 3,600 seconds plus 40 minutes. Now 40 minutes to convert to seconds, you just multiply by 60. So you have 40 times 60. And that will give you, all right, so we have the total here, okay, to be 6,000 seconds. So now we come back to our equation, which is quantity of heat energy equals power times time. So we have 50 times 6,000 or multiply by 6,000, and that will give you the quantity of heat energy here to be 3 times 10 raised to power 5 joules. So that's our answer. Now, the next thing we're going to be talking about is measurement of heat energy from an electrical appliance. Now, all you need to understand there is that whenever we have an electrical appliance involved, the quantity of heat energy is equal to the electrical energy. All right, quantity of heat energy equals electrical energy. And the electrical energy equation, we have three of them. Electrical energy is equal to IVT. We also have the electrical energy equals I square RT. Electrical energy equals V squared T over R. Now, I stands for current. V stands for the voltage or the potential difference. T stands for time. R stands for resistance. So you can write it down. I is current. Okay. Current is I. And then V is potential difference or voltage. R is resistance. Okay. R is resistance. Resistance. That's R. Okay. And T in our equation is time. All right, time is T. Okay, so that's just it. Now, the equations we are going to use whenever we have an electrical appliance involved, we have IVT equals MC. Remember we say electrical energy is the quantity of heat energy. So in place of Q, we're going to have IVT, and this is going to be, rather than say Q equals MC delta theta, okay, rather than say Q equals MC delta theta, we're going to say IVT equals MC delta theta, I square RT equals MC delta theta, V square T over R equals MC delta theta. We'll replace Q with electrical energy. Now let's see an example. The equation to use actually from here depends on your question. Some questions, they can give you current and resistance and time. Is this one, you're going to use this one. If they give you maybe current, potential difference and time, the first equation. So let's see our question here. It says an immersion heater rated 2 amps. So current was given to us to be 2 amps. Okay, 2 amps, 240 volts. That's our immersion heater. So we have potential difference, or the voltage, to be 240 volts. All right, it's used to boil water from 52 degrees Celsius to 100 degrees Celsius. So we have initial temperature to be 52 degrees Celsius. All right, to a new temperature, or final temperature, to be 100 degrees Celsius. All right, they said if the mass of water is 2.5 kilogram, so they give us the mass also to be 2.5 kilogram. They said determine the time taken to boil the water, so we're looking for time. All right, now you observe that, okay, they also gave us the specific capacity to be 4.2 times, it should be 10 raised to power 3 joules per kilogram per Kelvin. That's the specific heat capacity of water. Okay, so we have specific heat of water to be, can just write it as 4,200. Okay, still the same as 4.2 times 10 raised to power 3. So say 4,200 joules per kilogram per Kelvin. Alright, so now moving on, we have I given to us, V given to us, and we are looking for T, and it's relating to the specific capacity. Okay, so the equation that relates IVT and specific capacity is IVT equals MC delta theta. So this is the equation we are going to use to solve this problem. So we're going to have IVT equals MC delta theta. All right, and I is 2 and V is 240 multiplied by time. We said determine the time. We're looking for the time actually, so time is unknown, equals the mass, which is 2.5, multiplied by the specific heat capacity, which is 4,200, multiplied by the temperature change, which is final temperature minus initial temperature. All right, so that's going to be 100 minus 52, which is 48. So we have multiplied by 48. So to get T, we divide both sides by 2 multiplied by 240. All right, so that this will cancel out. There will be left to just T. So we say all over, divide both sides by this. So times 240 all over 2 times 240. So this will cancel the whole of this, and then we are going to have T equals 2.5 multiplied by 4,200 multiplied by 48 divided by 2 times 240. All right, the time we divide, we're going to have the time to be 1050 seconds. So that's our answer there. Now moving on, this question here says an electric kettle with negligible heat capacity is rated 2000 watts. An electric kettle with negligible heat capacity is rated 2000 watts. All right, 2000 watts. Wattage is talking about power. Okay, power is, what is the unit for power? So we have power given to us to be 2000 watts. It said if 2 kilograms of water is put in it, so we have mass, so be 2 kg is put in it. They say, how long will it take the temperature of the water to rise? How long is talking about time. Okay. How long will it take the temperature of the water to rise from, we have initial temperature to be 20 degrees Celsius to a new temperature, final temperature to be 180 degrees Celsius. All right. So our temperature change, which is delta theta, equals final temperature minus initial temperature, which is going to be 180 minus 20. That will give us 180 minus 20. We have the temperature change to be 160 degrees Celsius. Okay. Now they also gave us the specific heat capacity to be 4,200. That of water to be 4,200 joules per kilogram per Kelvin. All right. So how do we go about this question? This is also a question that relates specific heat capacity, but in this case, they didn't give you power. They didn't give you the quantity of heat energy. All right. We are supposed to have Q equals mc delta theta. But then what they give to us here is P and they give us time. But do not forget, in this same lesson, we said earlier that power is the rate at which work is done or energy is used up. Alright, so power is also equal to the quantity of heat energy all over time. And from here, we're going to have quantity of heat energy equals power times time. Alright, so rather than writing Q here, we can write PT. Alright, so we'll have PT equals mc delta theta. So P is equal to 2000 multiplied by time, which is equal to, and then equal to the mass, which is 2 multiplied by the specific heat capacity, which is 4,200, multiplied by the temperature change, which is 160. Alright, so to get the answer now, we divide both sides by 2000. Alright, so that we can cancel out this and then we get T equals this. So we have all over 2000. This will cancel this. We'll divide this side 2 by 2000. And that will give us the time to be equal to 2 times 4,200 multiplied by 160 . Okay, divided by 2000. So that will give us 672 seconds. Now the next thing we'll be talking about is the latent heat. Now the latent heat is simply the heat absorbed or given out by a substance during a change of state at constant temperature. Now this is the unit of measurement, joules per kilogram. Now remember when we talked about specific heat, we said is the heat that involves change in temperature. Okay, the heat that involves change in temperature. Now latent heat on the other hand involves what? Change of state. All right, very, very important at constant temperature. Now latent heat can either be specific latent heat of fusion or specific latent heat of vaporization. Now the specific latent heat of fusion, whose symbol is small letter L, all right, small letter L is a symbol for specific latent heat of fusion, lowercase letter, all right, is the quantity of heat required to change a unit mass of substance at its melting point to liquid without a change in temperature. Specific latent heat of fusion is the quantity of heat required to change a unit mass of substance at its melting point without a change in temperature. And mathematically, we have the quantity of heat equals mass times the latent heat of fusion, the specific latent heat of fusion. Alright. Now we also have the specific latent heat of vaporization, which is capital letter L or uppercase letter. And this is the quantity of heat required to change a unit mass of substance from liquid at its boiling point to vapor without a corresponding change in temperature. Alright, specific latent heat of vaporization. And mathematically, the quantity of heat energy is equal to the mass times the specific latent heat of vaporization. Now, looking at this problem here, it says 10 raised to power 6 joules of heat. Alright, 10 raised to power 6 is talking about the quantity of heat energy. So we have quantity of heat energy given to us to be 10 raised power 6 joules. All right, of heat is required to boil off completely 2 kilograms of certain liquid. Mass of liquid is equal to 2 kilograms. Okay, he said neglecting heat loss to the surrounding. What is the latent heat of vaporization? All right, don't forget latent heat of vaporization is uppercase letter L. All right, so we are looking for this. Okay, so it's very straightforward. We just go to our equation, which is Q equals ml. To get L, we divide both sides by m. All right, so first let's substitute. We have 10 raised to power 6 equals m is given, which is 2 times L, which is 2L. So to get L, we divide both sides by 2, all right, which is our mass. So we have 10 raised to power 6 all over 2 equals 2L all over 2. This will cancel this, and then you're going to get L to be equal to, we have 10 raised to power 6 divided by 2, which is 5 times 10 raised to power 5. All right, unit for latent heat of vaporization is joules per kilogram. Do not forget, we said latent heat, whether it's specific latent heat of vaporization or specific latent heat of fission, is measured in joules per kilogram. So that is our answer to this question. Please make sure to subscribe to the channel, like the video, and drop a comment.